Hi, here's a quick review video. Sorry about the quality. To try to review assigning voltages and currents and how it all applies to an op-amp. Now let's have a quick review. If I have a two-terminal device with node 1, node 2, and I assign VZ plus to minus in the direction of the current, I have Ohm's law. And I can write IZ as V1 minus V2 divided by Z. Now if I have the current going opposite, I still have Ohm's law, but the current is negative. And if you work it through, you'll see that IZ equals V2 minus V1, which is what you would get is if you reversed the plus and the minus, right? And had the current going that way. Oops, excuse me, getting a little bit out of focus here. All right, and if you look, right, I can have plus minus, and I get IZ equals V2 minus V1 divided by Z. And again, for completeness, if I put the current opposite to the voltage drop, right, I get V1 minus V2. These are all valid ways of doing it as long as you're consistent in assigning it. All right. Now, is this, if I have plus minus and I have the current going that direction, that's an okay definition. But if you happen to write that the current is equal to V2 minus V1, that is not okay. So you got to make sure that even though if you assign this properly or just assign it, that you have to write that branch current properly. Now I'm gonna scan these and send it out, but the question is this valid? This assignment and that equation? Is that one valid? Well, not to keep you in suspense, but both are valid. Now let's try to apply this to the inverting op-amp. And again, I'm going to kind of go through this pretty quickly because you'll have these notes scanned and sent to you. All right. So I have sorry, I'm not focusing very well. I have the input. This is just a classic inverting op-amp. But because I'm going to be drawing it many times, I really just want to work with these two resistors, and that is always assumed to be 0, that current. So really I can just write this out, X and in, and I have these current directions. In this particular example, I1 is in the node, I2 is out of the node, therefore I1 equals I2. And then I can write my branch currents. Right? In this example, they're both going into the node, but I still got plus minus plus minus. And when I run that through, it's I1 plus I2 because they're both going into the node. When I rearrange it, I get the same equation. Now I'm going to have the one coming in the node, one coming out of the node, plus minus, but minus plus. Well, I just have to change this to a minus sign, and ultimately you get the same value. And so if you are asking me how can you improve your grade or what to study for, do all of these, all right? Because you're going to get the same answer, but if you do them that many times, you can't possibly make a mistake with it anymore. But remember, right, we have Ohm's law, the current flowing from positive to the negative. IZ will equal VZ divided by the Z, and when it's opposite, Ohm's law, you just get a negative. You should get the same answer every time. Might seem a little tedious, but with that kind of practice, it'll just become second nature to you, and you won't have to think about it on an exam. Some things you do have to kind of memorize or even get that pencil strokes into muscle memory. All right. Now let's assume Rn equals 0. Calculate Vout or Vx if open loop gain is not equal to infinity. In this case, Vout is always equal to minus open loop gain times Vx. So if we substitute it into our equation, Ultimately, we get Vx. We get the exam solution. If open loop gain were infinity, you can see that going to infinity would drive Vx towards 0, or very, very close to 0. So let's rederive with voltage division and superposition, right? And what do I mean by that? With the superposition, I've got two voltages here. So I've got Vx, I apologize. I've got Vx depending on Vin, R2 divided by R1 plus R2. And then I've got it dependent on Vout, R1 divided by the sum of R1 and R2. And I plug that in. So do that and prove that they are the same. Again, these notes are with the understanding that you were wanting to understand this more deeply. Now, what is Vout if the open loop gain is 100? Well, now I solve for Vx. And yeah, I know a lot of times people will just say, oh, open loop gain goes to infinity, Vx equals 0 right at that point. But we talked about that in a previous lecture where you can't really say that just yet. I plug it all in. You can see my equations. And there it is. Vout equals -1, 1 over R2, 1 over open loop gain, R2, 1 over open loop gain, R1. And if this goes to infinity, these drop out. And yeah, you get the classic minus V and R2 over R1. So derive Vx and Vout for inverting and non-inverting. Do it three ways. Do it the superposition way, and remembering that the inverting, you end up having Vout and Vn. I guess it's not there. But the non-inverting, one of those inputs of the resistor is tied to ground, so you really just have one voltage division. Then have the currents going this way, plus minus, plus minus. The currents going the opposite way, plus minus, plus minus. So this would be voltage divisions. These two would be nodal analysis with your branch currents. Good luck. Stop.